is to start from here, bubble sort. So bubble sort also compare items and swap when the item not in order, but it carry out in a different way. So every time also shorten the unsorted number list by 1 and extend the sorted part by 1. Then we repeat until there's no more swap carry out, or until for array n elements, until we have carry out n minus 1 step. All these are important things. You will be tested on all these. Certainly you will be tested on this. So and the accurate presentation and answer is very important. Okay, so this is we use the same array to discuss bubble sort. This is the initial list. Okay, so what do we do then? We start from beginning. And we compare element 1 and 2 as what is stated here. Okay, all these are very important. Once you miss one, it'll be harder for you to understand. So I hope that all of you pay attention. 14, so compare element number 1 with element number 2, starting from left. Okay, so if they are not in order, because we want to sort the array in ascending order, so if they are not in order, we swap them, change their position. In this case, are they in order? Are they in order? Can I have a quick answer here? I think it's better to be interactive. Otherwise, now it's night. I'm not everybody tired, including me. So, as I said, if you don't follow, you miss one step. That means from there onward, even later, you want to catch up will be harder. So this is the nature of, because it is very much technical and the steps are very detailed. So, are they in order? Element 1 and element 2? Are they in order?
No.
Not in order. 14, 20, are they in ascending order? They are in order, so we don't swap them in this case. Nothing needs to be done. There's no swap is needed. So every time we compare two elements, okay? So the first time compare element number 1, element number 2. The second step we will compare element number 2 with number 3. So we proceed by one number. Okay, now we compare element 2 and 3. The first step, okay? So in the first step, the first task is to compare element 1 and 2. The second task will be 2 and 3. After that will be 3 and 4, 4 and 5, etc. Until you reach the last element. Okay? So if they are not in order, we will sort them. Okay, now we compare, after you compare element 2 and 3, 2 and 3, and 3 not in order, so we swap them. 2 and 3 not in order. You can see that when you compare 2 and 3 in the second task, or step 1, not in order. The one smaller is behind, bigger is in front, so not in order. So we swap them, swap 20 and 7. Okay, bring them into order. Okay, then after that we proceed. Every time we proceed by one element, just now I say, right? Then after we compare 2 and 3, after we sort them, proceed to compare 3 and 4, element 3 and element 4. Okay, so they are not in order. Again, we sort them. We sort them. So you repeat. Okay, after we compare these two in order, sort them. Then the next one we compare this one. The next one we proceed by one number. 8 we compare 20. After we swap this 2. Then we compare 20 with 5. Then if it's not in order, in this case not in order, we will sort them. Sort them, then after that, we'll move one element forward to the right again and compare until the end. Compare until the end, okay? The last two. Okay, so here, compare this element with this element in position, sort them, right? Then still carry out, still compare. We still have one number not totally untouched yet. So now the next one is to compare 20 with 13. Compare 20 with 13, then we not in order, we swap them. So this is now we have completed step 1. This is step 1. And in step 1 is also called cycle 1. And in for bubble sort, one step or one cycle is also called one pass. Okay? So now we have completed one pass. And this is the result of the first pass. After the first pass, the input array will change to this one. Okay? The number in the input array will change to this one. So this is the result of step 1. Okay? So if the question asks you to show the result of step 1, you have to show exactly this one. Everything have to be in order. Everything have to be in exactly. Every number has to follow this order. So this is the result of step 1. So, and you can see that after step 1, okay, if you want to sort the array in ascending order, after step 1, you will push the highest value right to the end. After one pass of bubble sort, you push the element with the highest value to the end. Okay. So that means that the last element will be in correct position. Okay, so for bubble sort, the sorted part is from the end of the array. Okay, so that is different from insertion and selection sort. Yeah. Sorted elements starting from left. For bubble sort, we start from the sorted part, start from right. Okay, so that means now after we finish pass 1, this element is sorted. That means this is a sorted area. It means the unsorted number is reduced by 1. So the unsorted part of the array is reduced by 1, in other words. So now we have to continue, proceed to the next. So we have completed. So the first pass is complete. Okay. It means this is the result of after the completion of the first pass. So now we proceed to the second pass. That means the second step. Second step, we will do it again. Do the same thing again. Okay? Start from left to right. Each time we compare two elements. If they are not in position, we sort them. So we start from here, and every time extend by one element. That's just what we do. Okay? Until we reach here. So the second pass, under the second step, we compare second element with the third element. Not in position, we sort them. After you sort them, then compare third and the fourth, etc. Until we reach here. Until we reach here. Until we reach here. Okay? Do we need to proceed to here? No, because after the first step, the last element is definitely in correct position, so we don't need to proceed. We don't need to move to the last element. Okay? So not in order, we sort them. After we sort them, then the sorted part will be extended by one element. So now, after we finish the second step, okay, the sorted part, the number of elements in the sorted part, is extended by 1, and the unsorted part is reduced by 1. Here, reduced by 1. Okay, so we continue with all these steps. So this is the result of second pass. If the question asks you to show the result of each pass, then you should not show all this. You should not show it. You should show just now that one. If the question asks you to show the result of each pass, you should show. This one should be the first one to show. This one is the first pass, and this one is the result of the second pass. Okay, etc. Okay, until the whole array is sorted. Okay, so this is now we go faster. So after the third pass, this is the result. This is the result. That means again the sorted part will be extended by one element, and the unsorted part will be reduced by one element. Okay, so we continue this way. Every step, every pass, the sorted part extended by one element, and the unsorted part is reduced by one element. Okay, now this step is something different. You can see that. You see from here that okay, from this step to this step, then from here to here, compare 14, 15, then after that compare 5, then 5, 7, 8, 6. Okay? So we carry out a swap here. For this step, from here to here, we do some swapping. From here to here, we also do some swap. These two, for example, these two swap. From here to here. Okay? From this step to this step, we also do some swap. We swap these two, right? Can you see that? Can you see? From this step to this step, we do some swap. Okay, and from this step to this step, do we do any swap? From here to here? Yes or no?
No.
So from here to here, there is no swap carry out. So there's no swap carry out, that means we can stop. After we get the result for this pass, we can stop because there is no swap. If there are some more swap carry out, okay, then we will have to go for one more steps. But since from here to here, there is no swap, so we are finished. We have finished sorting this array using bubble sort. So for array of 10 numbers, just now we complete how many steps? Just on this case, you complete how many steps? How many steps? Here, 1 steps. This step 1, right? Step 2. Then this is step 3. Step 3. Then after that, over here is some. Okay, these are the number of steps, all the steps shown here. 1, this first pass is complete. After first pass, the first element is in position. this show the result every steps. So how many steps involved? Here, for array of 10 elements, how many steps involved?
9.
Here, this is the second step, right? This is the result. Second step is the third, fourth, fifth, sixth, seventh, eighth. After you produce that means for this case we have only done 8 steps. Because why? Because the last step there is no swap. Okay, the last step there is no swap from here to here. There is no swap, so that's why we stop. There is no swap, meaning the numbers all are in order. So there is no swap. But if the last step also still have some swap, then we will have to carry out 9 steps. Okay? So here we only have 8 steps. It's because the last step there is no swap. We stop. Yeah. So bubble sort, there are 2 conditions that we can stop. For array of n elements, yeah, if you have completed n minus 1 step, definitely you can stop here. So all the elements will be in position. For array of n elements, if you have completed n minus 1 step, definitely you can stop. Another condition to stop is when there is no swap in the previous steps. We also stop. That is how the bubble sort work. Okay, take for example, okay, if you do a bubble sort, yeah, for this array, okay, what is the result? Step 1. For step 1, every time we change 2 elements, right? If you start from here, not in order, we sort them, right? So 1 change with 2. Then after that, 2 will be compared with 3, right? We'll compare 3 in order, right? In order, so no swap. So then 3 will compare with 7. Is it in order?
Yes.
So no swap. Okay, so the first, after you complete the first step, the first element, okay, we underline the sorted element. Underline the element in the sorted part. So after you complete the first step, the last element is sorted. Last element is sorted. Then step 2, okay. So although it's in order, of course, visually you can see in order, but when you perform bubble sort, yeah, you cannot stop here. You cannot stop here. You have to wait until, because for this case, n minus 1 is 3, right? 3 steps, or there's no swap carry out. Yeah, there's no swap carry out in the step. Then you stop, because there's a swap. There's a swap, right? That's not when we do 2, we swap 1, so cannot stop. Then step 2. Okay, so we still carry out step 2, compare again, compare these 2 in order, compare these 2 in order, okay? So you compare until all the elements in the unsorted part are compared, then that means that this step is finished, okay? So this element is sorted already. And no swap. Okay, from here to here there is no swap. So that means all the elements are sorted. No swap means all the elements are sorted. If some elements are not in order, definitely there will be some swap in the steps. So altogether there are 2 steps. We have to carry out 2 steps for sorting this array. Okay, and at most you need 3 steps. Okay. Well, after you bring all the elements in position, if only left one element in the unsorted part, definitely the whole array is sorted. Okay. So need at most only need n-1 steps. Okay. How hard is this? For array we have to complete 9 cycles, and for every cycle we perform 1 less comparisons. Just now we can see that the first round for array n element, the first round we do how many comparisons? Every time we compare 2 elements, right? So every 2 elements. So for array n elements, every time we do how many for the first step we do how many comparisons? For an array n elements. Every time we compare 2 elements, right? Then compare this one with this one. Then after that, this with this, right? And compare until the end, right? How many comparisons?
N equals to n, is it? N minus 1, yeah.
Every year increase by 1 element. So start from here. N minus 1, right? The first step we do n-1 comparison. The second step, because the last element is sorted, so we do n-2 comparison, right? So until towards the end, we do only 1 comparison. Okay, so for array of 9 elements, for array of 10 elements, the first round do 9 comparisons, after that 8, after that 7, reduce until 1. If we have to carry out 9 steps, but just now we save 1 step because the 8th step, during 8th step, there's no swap done. This is the maximum number of comparisons. So, what is the maximum number of swap? So, for array of 10 elements, altogether this is the amount of comparisons, maximum number of comparisons. So, what is the maximum number of swap? You'll be 45 also, right? Assume if every comparison you find they're not in order, then you'll be 45 swap also. So for array n elements, basically it is the number of swap and number of comparison is the same. It's the same. Okay. So that is for array n elements, the number of comparison will be n-1 plus n-2. Plus 2, 3 plus 2 plus 1. Okay, this is the total number of comparisons. Okay, so 1, 2, 3. In other words, if you look from this side, 1, 2, 3, plus until n-1. As the other day I told you, this is an arithmetic series because every the succeeding terms and the preceding term always have different 1. Always a different 1. So we can use a formula, right? A plus L, last term plus first term divided by 2, times the number of terms. Sum. So this sum, we can use this formula to compute last term plus first term. Last term in this case is 1. First term is n-1. n-1 plus 1. Last term plus first term. Divided by 2 times the number of terms. How many terms here? n-1 term. Okay? So this is the this is n-1 plus 1 means n. So it's n times n-1 divided by 2. So this is the total number of comparisons. Okay? At most, for purpose of this, the maximum number of comparisons. The maximum number of swap is the same. It's also this this number. Okay, again, the number of operation we carry out is about n squared. What's the meaning of number of operation? Means number of in this case there are two kind of operation. One is comparison and the other one is sort. So the total number of operation means the total number of sort plus the total number of comparison. So it's, these two add up together. N times n divided by 2 plus n times n minus 1 divided by 2. So they add up together is n times n minus 1. So it's n squared minus n. Okay, n squared minus n is approximately equal to n squared. We ignore the lowest term. In performance analysis, we only interested to look at those cases with large n. So usually we will ignore the lowest, the term with the lower degree. Only consider the term with a higher degree. So in this case, this is a term with a lower degree. This term, so we drop it off. Don't consider, only consider the term with a higher degree than n squared. That's why we say it's n squared here. Okay, so you notice that for selection sort, for insertion sort, and now for bubble sort, yeah, the number of operation is all in terms of n squared. So selection sort uses half as many in the worst case. Okay. But selection sort, it does not mean that selection sort, in terms of total number of operations, selection sort is about n squared divided by 2. But it does not mean that selection sort is definitely better. But because in this case we are talking in terms of the worst case. Yeah. For best case, as you can see from here, for best case, if the element in the array is almost sorted, yeah. So if we do a bubble sort, yeah, even array of 10 elements, yeah, if only 2 elements not in order, we still need only 1 step. We still only need 2 steps. Yeah. But for selection sort, we will still carry out if an array of 10 elements, okay, if it's only 2 of them not in order, in this case, for bubble sort, we only carry out 2 steps. But for selection sort, we still carry out 9 steps. We still need to carry out 9 steps. So if the element in the array is almost in order, usually bubble sort and insertion sort are better. Okay, but all this all in terms of n squared. Does it mean that we cannot do better than n squared? No. There are some sorting method that can complete better than n squared. That means the total number of operation is less than n squared. It's n log n. Yeah, there are sorting method that can finish it by doing n log n operations. Okay, the sorting merge sort is the one who can do it faster, about n log n. But we are not going to study merge sort here. But we are going to study one more sorting method, that is quick sort. Quick sort, the worst case is still n squared. Okay, but usually the quick sort, most of the time we need to carry out n times n log n operation only. We are going to study quick sort now.
Why is it A plus L divided by 2 without number of elements?
Huh?
What the sum? Why is it the first?
Where?
Uh,
I put
why is it A plus L divided by 2?
which one?
This one.
Oh, why? Array time.
The
What's
one
first L,
is the first element plus last element.
Number of term. Okay, array is n minus 1, right?
Yeah.
So that's these are. L is the.
Among the 4 sorting methods we
Oh,
study,
I think L is
quick
because
sort
there's
is,
only
I guess quick
one
sort
thing
is the
inside one
hardest.
box.
It's harder
So
to
it's one.
understand.
Oh.
There's
So the other 3
Oh,
sorting method,
yeah.
I guess if you pay attention,
Then you just
Close that
input the value into
you
the
should,
formula.
by now you should
Oh,
Times.
this is the
understand
formula.
what they are
Yeah.
doing.
You must remember.
Okay. Get it?
For this,
Oh.
The other three
particular
sorting method, insertion sort, selection sort,
Huh?
and bubble sort. Quick sort is a bit more harder. But
I can
think,
send you this if you want.
uh, So the quick sort is a little bit more difficult to understand. So partition the list into 2 parts. So quick sort is all based on partitioning. Every step is one partitioning. So as far as you understand partitioning, you just apply partitioning accordingly.
Huh?
You can do quick sort. So partitioning is based on the first element. So based on the first element, partition the array into 2 parts. Okay, partition the array into 2 parts. The first part, we have all the elements lower than the value. The last part, we have all the elements higher than the value. And we keep repeating partitioning. Okay, so now we shall take a look at partitioning. So this array, this is 4, 8, 3, 5, 7, 2, 1. Four, 8, 3, 5, 7, 2, 1. This is array. Okay, now we want to do partitioning. Now we want to carry out partitioning process for this array. So it means that after the partitioning, the first element will be in position. Then the array will be divided into 2 parts. The first part will contain those elements lower than the first element. The second part will contain those elements higher than this value after the first partitioning. So, and this element, okay, in partitioning, we call this element a pivot. The first element, we are going to base on this element. This element is assigned as the pivot, and we have, okay, for the remaining element, always the first element is assigned as a pivot for the partitioning. Then we have 2 pointers. Head will point to the first element, the first of the remaining element, and tail will point to the last. So for the first element is taken as pivot, and for the remaining array, the first element, we have a pointer. The head pointer is pointing to the first element. That means the first element is the head, and the last element is the tail. Okay? So now we can start the partitioning process. Then okay, so partition, we have a head and tail. This is the head and this is the tail. So So the head, the value is, pointer is here, the value is 8, and the tail, the pointer is 1. So now we proceed partitioning. This is the process of partitioning. Now, we compare pivot with the head. If pivot is larger than the head, then we move the head. If pivot is larger than the head, then we move head to the right. That means move the head pointer to the right. Compare pivot with the head. Is pivot larger than the head now? No. It's not, right? So that means we don't move the head. Don't move the head one position to the right. So the head is untouched. And so the if condition here is not satisfied, we don't do this. We do the second pass here. So since the head is not larger than the pivot is not larger than the head, so we go to step 2. Okay? If the head is if the pivot is larger than the head, we will move the head to the one step. Move it one position to the right, and we will go through the step 1 again. Compare pivot with the head again. But now since the pivot is not larger than the head, so we don't carry out this. We don't carry out this. We don't carry out this. We will do this. We'll go to step 2. Go to step 2. What do? We will compare pivot with the tail. Pivot with the tail. Compare pivot with the tail. If it's smaller than the tail, if pivot is smaller than the tail, pivot here, tail is smaller. Is pivot smaller than the tail?
No.
No, right? So it's not smaller than tail. So we don't follow this also, because does not satisfy this condition. We go straight to, since it's otherwise, so we move to step 3. We consider step 3 now. So head and tail have met, head and tail. Later you will see that when we carry out this task, we will move head more and more to the left, to the right, and move tail more and more to the left. There will be a time that they meet or cross each other. Okay? So step 3 is to check such a condition. But at this moment, they have not met, right? And they have not crossed yet. Yeah. So nothing done. For step 3, if it's nothing done over here, we go to step 4. Go to step 4. Step 4, what do? Swap the value of the head and tail. Swap them. So now we proceed to step 4. Step 4, we change the content of the array. We swap the. Okay, now we swap the head and tail. 4. 4 is here. So swap head and tail. 1 should be here. Swap the value head and tail, swap them. So 8 should go here. The rest remain unchanged. So we swap the head and tail. The rest remain unchanged. Not only that, then we move head to the right, move tail to the left. Move head to the right, that means now move one position to the right. Now the head become here. Tail one position to the left. Tail is here. Okay. So this is for step 4. And go to step 1. Okay. After you do this, you go to step 1. Do the same thing just as we have done. Okay. Go to step 1 means compare the pivot with the head. Compare pivot with the head. Pivot is still the same. Pivot all the time remain unchanged. So this is a pivot. Compare pivot with the head. So now, is pivot more than the head? Is pivot more than the head now?
Yes.
So pivot is more than a head, so we move it. So that means we have to follow this. If pivot is more than the head, is larger than the head, we have to move head to the right. move to the right. That means move one position forward. We have to move head here. Okay, and we have to repeat step 1. It means you have to do this one. You have to compare pivot with the head again. Okay, so now we compare pivot with the head. Now head pointer pointed here. That means the value of the head has changed. So now it's pivot more than the head. So pivot now is no more than the head, yeah, because pivot is 4 and head is 5. So we don't do this. We don't do this. When you go back to step 1, we compare with, and then since it's not satisfied this condition, we go to step 2. Step 2, we have compare pivot with the tail. Pivot with the tail. Okay? So is pivot less than the tail? Is pivot smaller than the tail?
No.
So pivot is not smaller than the tail. So that means nothing is done here. Nothing is done here. We go to step 3. Step 3 again, we will check whether head and tail is made. They have not made yet, right? They have not made or close yet. So then we have to go to step 4. Step 4, what you do? What do you do? Step 4, we will again. Step 4, we have to change the content of the array. 4 here 1 remain 1, then 3, then okay, under step 4, we will move head to swap the value of head and tail. Swap the value of head and tail now. Now the value of head and tail is these two values. Here we swap them. So head here become 2, and here become 5. Okay, and move head one position to the right. And move tail one position to the left. So now head and tail has already met. Yeah. So after step 4, you can see that you have bring head and tail to the same position, going to the same element. Okay. So now we go back to step 1. Follow. We go back to step 1. Now we compare pivot with the head. Pivot with the head. So pivot is 4. Still 4. Head is 7. Pivot with the head. Pivot is not larger than the head, right? So pivot is not larger than the head. In fact, it's smaller than the head. Yeah. So nothing is done for step 1. But so we move to step 2. Step 2, we will compare pivot with the tail. Tail is also this element. Compare pivot with 7. So is pivot smaller than the tail? Is pivot smaller than the tail? Yes, right? So yes means you have to move tail one position to the left. So tail is here now. Okay? So now not only men, they have claws. Head and tail has a claws. So now again you compare. So after you since just now we compare, satisfy this condition. So and we move tail to one position to the left. So we have to repeat step 2. We compare pivot with the tail again. Pivot with the tail. With the new tail. Here is 2, right? Pivot is not smaller than the tail, right? Now it's not smaller than the tail. So nothing is done. So we go to step 3. Okay? Step 3, what's done in the step 3? Step 3 will check the condition. Whether has head and tail has made a clause. Okay? Now we satisfy this condition, head and tail has really clause. Clause, right? Clause, head, tail move to, tail is on the left of the head. That means tail and head have already clause. Okay? So satisfy the condition for step 3. So that means we have to swap pivot and the tail. Swap pivot with the tail. So that means now we have to swap them. Swap these two. Swap these two, and again will change. 1, 3, 2, so pivot with the tip. 2 come here, 4 come here. Okay, the rest remain unchanged. So this is the result of one partitioning. So after first partitioning, you'll find that the pivot is in sorted, is in correct position. Okay, the pivot is in sorted position. Then the rest, those elements at the left of the pivot is smaller than pivot, and those elements at the right of the pivot is larger than the pivot. Okay, so pivot is element in correct position after one partitioning. So this is how we do for quicksort. Yeah. So one partitioning is one step for quicksort. So that means this is just the result of one step for quicksort. Then what is the next step for quicksort? For quicksort, then the next step, that means you will do a partitioning for this subarray, for this part only. Do a partitioning for this part. Then you will keep doing partitioning for subarray. The array getting the array that you have to do partitioning will be smaller and smaller. Okay, so once you reach once your subarray is only one element, then that means that you don't need to sort. After you finish the left subarray, then you'll do the same thing. You'll do the same thing for the right subarray. Do a partitioning for this one. Then after that, this array is further divided into subarray. Then do partitioning again until all the elements are sorted. So that is how quicksort works. Okay, this one we have explained just now. Okay, so eventually this is a result of one partitioning. One partitioning is one step in quicksort. Here give an example. Okay, on a bigger array, yeah, here this is the same array just now we apply bubble sort. Yeah. So the first element is always served as pivot, and after one step, yeah, the pivot will be in correct position and divide the array into two parts. The first part will be smaller than pivot, the second part is larger than pivot. So this is one step in quicksort. Every quicksort is one partitioning. So after that, you partition which one? After this, which one you partition? After this, we partition the left subarray first. We partition this first. When you partition this, the first element in this subarray is served as pivot. The first element is served as a pivot. You can see after you partition for this one, then this is a result of applying partitioning to this part. 6, the pivot is in correct position. Then again, array divided into two subparts, first and second part. Okay. So now we apply partitioning again. We always do the left subarray first before we deal with the right subarray. Okay, now after this, you divide this subarray. After the second partitioning, you divide this subarray into two parts, right? The first part is only 5. The second part is this 3 number. Okay, so the first subarray is only one element. One element definitely in position. Yeah, you don't have to do anything. Okay. The second step, you partition this one. when you do a partitioning for this one, you divide this subarray into two subarray again. This one and this one. Yeah, the first one is has only one element. Okay, there's one element, that means definitely it's sorted. You don't do anything. So, and the next partitioning will be on this one, on this subarray, on the right hand side, because the left hand side you don't need to do anything. Okay, then we have to do another partitioning. Okay. Then after you do a partitioning, again the first element in position, and divide the array into two subarray again. In this case, the two subarray, the left subarray is nothing empty, only the right subarray. Right subarray have two elements. Then we have to carry out a partitioning for this one. Okay, partitioning for this one. When you do a partitioning for this one, again you divide into two subarray. The left subarray is empty, and the right subarray only one element. One element means you don't have to do anything. You don't need to do a partitioning for this subarray because it's only one element. Okay, so now the left subarray for the first partitioning is all sorted. So now we proceed to the right subarray. So left we always deal with the left subarray first, then deal with the right subarray. Now we deal with this part. Do the same thing. Okay, do the same thing until all the elements are sorted. Okay. So this is how partitioning is. This is how quicksort is carried out. Okay. Not too difficult, right? Not too difficult, right? Okay, this is how quicksort carry out. Okay, that's almost all for sorting. Perform a quicksort basically is about n times log n. Okay. Usually when you do a quicksort, the total number of operation is about n times log n. Right? So which one is larger? For others, why is n times log n? Because n times log n is when we have an ideal situation. Every time when you partition, so for n elements, every time when we partition, we divide the array into two almost equal. We divide the array into two almost equal subarray. We divide the whole array into two subarray with equal size, almost equal size. That's the ideal situation. If we can do that every time we divide half, so we'll finish it very fast. Very fast. That is about n log n. Yeah. You don't need to understand the detail of how to derive n log n for the optimum case. Okay, this is not the worst case, it's the optimum case. That means when the situation is ideal, every time you can divide into two almost half. So you don't need to understand the derivation. I just want to highlight to you the n and log n. And n squared. Which one is larger? N here, n is the number of operations, certainly is positive. So which one is larger? N squared is larger or n times log n is larger?
N times log n is smaller.
N times log n is definitely smaller because n squared is n times n, right? This n equivalent. Then log n is definitely less than or equal to n. Yeah. So log 2, 8, how much? 3, right? 8 is 3. So certainly log n is smaller. Okay. So for ideal situation, quicksort can finish it by by doing n time log n operation. Which one is the best? It depends on the, if we have a small number in the array, quick sort is overkill. Okay, so should not apply quick sort. The number of element in the array is small. Okay? So, and if it's disorder, if it's nearly in order, insertion and bubble sort are better. Just like because for bubble sort, although the maximum number of steps is n minus 1, but if there's no sort carry out in the step, we can just stop it. So if only small number item, usually insert sort is better. So it depends on what kind of array we are going to sort. Okay, that's all for searching and sorting. Any question? Okay, we have a 10 minutes break. After the break, we will go through it.